Good morning, everyone. Today, we are going to have a topic related to solution of difference equations. Okay, so with continuing what we had left in the previous class, in today's class, we are going to discuss regarding the solution to difference equations. Let me share my screen right now. Yes. Now, the topic that we are going to discuss in today's class is solution of difference equations. Solution of difference equations. If you had clearly understood what we had done in the differential equations, we had the derivative, that is d by dt, of output signal, that is y of t, what I'm going to write here. So we had d by dt of the signal, that is a output of the signal, that is y of t, in the continuous time domain. So a differential equation is valid for continuous time signal, continuous time signal or time domain. Let me categorize it as time domain. So now this continuous time domain, what is there? Either it might be an input signal or an output signal, it holds good. So the differential equation, what we are going to study, holds good for the continuous time domain. Now, in case of the discrete time domain, what I'm talking right now, it is x of n. So the x of n is the signal, that is the input signal, that is y of n, which gives rise to the output of any LTI system, or generally it is meant to be called as an output signal, that is y of n. So LTI system is one thing that when it passes, the input passes, you have the output, that is y of n. So x of n convoluted with h of n, right? So that is the convolution theorem that we have, or convoluting two signals that we have. So where h of n is called as the impulse response of the system. Now d by dt of y of t, which was referring to the continuous time domain, there we were classifying it based on the differential equations. We're classifying it on the differential equations. So one thing that is there, that is the differential equations. Second one, what we come across is the characteristic equation of the differential equation. So I have the characteristic equation of the differential equation written in format called as s power n a naught s power n minus 1 plus a1 s power n minus 2 plus an s power 1. Okay. Next, we had an minus 1, sorry, an minus 1 plus an, that would be equal to 0. The roots of the characteristic equation led to the natural response of the system. So why I have written it here as 0 is, without the absence of the input, we were writing the roots of the characteristic equation. So we were forming the characteristic equation earlier, and then we were coming to the solution of the characteristic equation. So once I have the roots of the characteristic equation depending on the highest power that we have, so say s1 and s2, so we had s squared plus 3s plus 2, certainly a equation when it is equated to 0, I have two roots that are being formed for s1 and s2. So this s1 and s2, whatever that is there, I will be having it called as the nature of the roots. Okay, so the nature of the roots is entirely dependent on the characteristic equation that is being formed, and the characteristic equation directly results in the differential equation that has been modeled. So now coming to the difference equations, I have the same terminology or a similar way where I can have. So first we are doing the difference equation. So first we are defining what is a difference equation. So there we are having a differential equation in continuous time domain. So this is a discrete time domain here. Discrete time domain. Now I have the discrete time domain. I have the difference equation being formed. So second one, I'll be having the characteristic equation also being written. I have the characteristic equation also being written. So now let me write it quite clearly. So once when I consider the nth order difference equation, difference equation with a single input, with a single input, with a single input. So now this difference equation, what I'm going to write, it's a nth order difference equation with a single input. You might be coming to a conclusion, what happens when I have two inputs, right? So once I have two inputs, I'll be having the difference equation being written in the next one. So if I have two inputs, say x1 and x2, so you can use a summer block and then you can have the output signal being written, or you can have the system being designed in such a way that you are having both the signals being present there. As of now, we are considering the single input that is being present there. So what I can write, I can have y of n plus a1 y of n minus 1 plus a2 y of n minus 2 plus an. So if I keep on extending, and I can reach y of n minus n. Okay, so I can write it as y of n minus n, that would be equal to 0. So an is the constants, a1, a2, a3 up to an is generally called as a constant that is being present there, along with the output, that is y of n in the discrete time domain. So we are considering the discrete time domain, and then we are writing the difference equations which is there for the discrete time domain. So y of n is the output, and why I have I should have written it as x of n here. So let me change it right now. So just before writing the characteristic equation, I can write x of n as the single input, that is this. Now the solution to the above difference equation, it can be written as y of n as the output. You have the natural response and also the forced response of the system. Response really means the output of the system. The natural response, I can write it here, natural response of the system, natural response of the system. So YF is called the forced response of the system, forced response of the system, and output y of n is considered to be the total response of the system, total response of the system. Hope you are clear with the terminologies what I'm using right now. Yn of n plus yf of n will gives rise to the total response of the system. So the first thing that comes to our mind is the natural response of the system. Natural response of the system. Natural response of the system. Okay, now I have the natural response of the discrete system written as yn of n. So yn of n can be written where you have the roots of the characteristic equation being obtained. So how do I obtain the roots of the characteristic equation? I can simply recall the difference equation what I had written earlier. So I had y of n minus 1 plus a2, a second constant, multiplied with y of n minus 2, plus I can have an, y of n minus n. So now, without the absence of the input, I can call such response of the system to be the natural response of the system. Okay, so now I can have the Z transform approach to find out the roots of the equation. So what I can do here is I can have these things. What I've written here is certainly called as the delay of the system, delay of the output that is being present there. So what I can do right now is I can have 1 plus a1 z power minus 1. So it has been delayed by 1 unit. Okay, z power minus 1 is a delay in the discrete time domain. I can write it as delay in the discrete time domain, discrete time domain, discrete time domain. I can write it like this, delay in the discrete time domain plus a2 z power minus 2, and I can certainly have z power minus n being written there, and I can equate it to 0. So now what I'll be doing here is I'll be multiplying with z power n. So capital N refers to the order of the system. N refers to the order. Okay, n refers to the order plus a1 z power n minus 1 plus a to z power n minus 2 plus up to an that is there. So I can equate it to 0. So this entire term forms the characteristic equation in z power n. So slightly being altered, I can have this equation being taken certainly to find out the roots of the characteristic equation. So the earlier one is also called as the characteristic equation. So once it has been changed in such a way that a slight alteration where you could have z power, the order of the system, that is capital N being raised, you will be having the characteristic equation being obtained. So now it becomes quite easy for me to write down the natural response of the system. The roots of the roots of the characteristic equation plays a major role in determining the natural response of the system. So I have a simple table where I can write it. So just before that, I have certain roots. If I say n roots, okay, if I have n roots, say z1 comma z2 up to zn, the natural response, assuming the roots to be non-repetitive in nature, I can write it here, assuming the roots to be non-repetitive in nature, so yn of n can be written as k1 z1 power n plus k2 z2 power n plus k3 z3 power n. Okay, and I can write up to kn zn power n. Okay, so I can write it like this: k1 z1 power n, k2 z2 power n plus k3 z3 power n up to certain strength. I mean certain the order of the system or the roots that are being present there. If I have two roots, I can just restrict it to two constants, say z1 power n plus k2 z2 power n. So that is the natural response of the system for two roots. Okay, so I can write it here for two roots of characteristic equation. Two roots of the characteristic equation. So I can write the natural response of the system. So once the roots are real and distinct and it is non-repetitive in nature, I can equate, or I can write the natural response in such a way that I'll be having the roots of the characteristic equation being written like this. Now, if certain nature of the roots are being there depending on the characteristic equation, so I can recall this table, what I'm going to write now: root of the characteristic equation, next structure of the natural response, so root of the characteristic equation, then you have structure of the natural response. First one, real and distinct. So I have r real and distinct. Okay, that is k r power n. Second one, I have complex conjugate. So once I have the trigonometric functions being present there, so r e power j omega, usually r will be having unit circle taken into consideration. So I have r power n k1 cos n omega plus k2 sin n omega. So I have this term being present there. So next I have real and repeated. So r being repeated, so you will be having repetitive roots, as I already wanted to mention in the continuous time domain. So here, in terms of the discrete time domain, you are going to have three such nature of the characteristic equation roots that are being present. I can have r power n, I'll be having k naught plus k1 n plus k2 n squared. Okay, so just see here, you are having k1 n power 1, k2 n squared up to kp n power p. So these are the roots of the characteristic equation. So depending on the roots of the characteristic equation, I have the nature of the response, that is the natural response, that is yn of n. Okay, it's entirely dependent on the roots of the characteristic equation. Now, in a similar way, once the input is included, I'll be having the forced response of the system. Forced response of the system. Forced response of the system, that is yf of n. So I have the forced response of the system, say yf of n. So now with the response of the system where the input is included, where the input is included or considered, or it is applied to the system, included. Okay, so once I say the input is included to a system, so what happens? So again, the forced response of the system is where you will be having the input that is considered, and depending on the input, I have the structure of the forced response being present there. So that is the nature of the input. Next, you have the structure of the forced response. Structure of the forced response. Structure of the forced response. So nature of the input, then you have the structure of the forced response. First one, a constant, say u of n. Generally, what I consider once you have a constant is called to be the unit step signal, generally, which is considered, and I have the structure of the forced response to be C1. Okay, C naught or any constant. Okay, any constant that is taken, I have C naught, you have the structure of the forced response to be C1. Okay, so next one, what you have here is alpha power n. I'll tell you a note which has alpha power n, that is later on, C times alpha power n. Third one, what I have here is cos of n omega plus beta. So what I have here is C1 cos n omega plus C2 sin n omega. I can write it like this. Fourth one, what is there is alpha power n. So 2 and 3 being multiplied, I'll be having alpha power n cos of n omega plus beta. Okay, I'll be multiplying it. What I can have here, I'll be having alpha power n cos of n omega plus, yeah, this one is C1 cos of n omega plus C2 sin of n omega. So that is there. Okay, so this forms certain set of inputs that are there, and next one, what is there is the next set of table. Again, I'll be having nature of input. Next, I have the structure of forced response. Structure of forced response. Okay, so first one that is there is n. Second one, you have n squared n cube, that is there. I can raise it to power p. So C naught plus C1 into n, C naught plus C1 into n plus C2 n squared plus Cp to the multiplied with n power p. Okay, so third one, you have n into alpha power n. Fourth one, what I have here is n power p alpha power n. So here I can write it to be alpha power n C naught plus C1. So here I can write alpha power n, where I be having it called as C naught plus C1 n plus C2 n squared plus up to the point Cp whole raised to the power n power p. So depending on the nature of the input, I'll be having the structure of the forced response being present here. I'll be having for n, I can have C naught plus C1 n. For n power p, I'll be having C naught plus C1 plus C2 n squared up to Cp n power p. So n times alpha power n, I'll be having alpha power n multiplied with C naught plus C1, that is there, C naught plus C1 n to make it into consideration. I'll be having n power p alpha power n. I'll be having alpha power n multiplied with C naught plus C1 n plus C2 n squared plus up to a point where you will be having plus Cp n power p. Now, an important note what I would like to highlight is an important note what I would like to highlight is if input x of n is alpha power n. Okay, I'll give an example. For example, what I can write it here is if x of n is 2 power n, yeah, where alpha would be equal to 2 depending on the consideration that I have there. So where alpha is the root of the characteristic equation. Alpha is the root of the characteristic equation. So if I have alpha as the root of the characteristic equation, and again what needs to be done, it is repeated m number of times, then if it is repeated m number of times, m times, okay, if it is repeated m number of times, then the forced response forced response must be multiplied by n power m, must be multiplied with n power m. Okay, as I already told you, the total response will be equal to natural response natural response plus forced response. The total response of the system will be equal to natural response plus forced response. And the constants, whatever that is there, that can be evaluated by taking the initial conditions into picture. So keeping the initial conditions in mind, I can have the constants that are being evaluated. Either it might be in the natural response or it might be in the forced response of the system. Taking the initial conditions into picture, I can evaluate the total response of the system. So yn, that is y of n, that would be equal to yn of n plus yf of n, that is there. So y of n, that would be equal to yn of n plus yf of n. So now I want to repeat once again, if the input is alpha power n, so any alpha power n multiplied with cos or n times alpha power n, that is there. So I have alpha being the root of the characteristic equation. For example, 2, like s squared plus 3s plus 2 if you have. So if I have 2 as the equation, s squared minus 3s plus 2, some equation I just wanted to write here. So I have s1 being equal to alpha. Okay, so at that case, what you can write is, okay, just one time. So it is repeated only once. Okay, it is repeated only once, and that is the reason why the forced response must be multiplied by n power 1. So it is repeated once. That's the reason why you can multiply it only once. So that is one important note that is there here. So where you can multiply it by n power m if it is repeated m times. Okay, so keeping all these things in mind, I can go for the numerical problems to find out the forced response of the following system. Y of n, that is the first problem what I'm writing here, 0.4 into y of n minus 1, that would be equal to u of n. Okay, so this is to find forced response of the system. So that is y of n minus 0.4 into y of n minus 1, that would be equal to u of n. Okay, so to go for the solution to a given problem like this, I can write down the solution quite easily depending on what is asked in the problem, that is to find out the forced response of the system. So what do I do here? That is yf of n. So that is the forced response of the system. Forced response of the system. forced response of the system. Now what I can write here is the structure of the forced response. Okay, the structure of the forced response is dependent on the input, that is u of n. So input is u of n here. So this is generally a constant. So yf of n is generally another constant called as c1. Okay, so I can write it to be yf of n, that would be equal to c1. There is no other n term being present. Yf of n minus 1. So depending on the equation that is there here, I can write it to be yf of n minus 1. Okay, so I can write it to be another constant called as c1. That is because n term, that is n minus 1 whole raised to the power 0, whatever may be the value of n, so that would be equal to 1 again, right? So now I can write it to be another constant, say c1 again. Fine. So now let me rewrite the equation what is given there. Yf of n minus 0.4 times yf of n minus 1, that would be equal to 0. So c1 minus 0.4 c1, so that would be equal to, so I can just make a change here. I was about to write c1. Okay, so I'll be having again, it is called as c1 there. Okay, another constant what I can generally refers to. Okay, so I can call it to be any other constant or 1. Okay, so yeah, depending on the input equation, I can call this to be 1 here. Okay, I can call this to be 1. I'll make a slight change. So c1 needs to be calculated, that is 1 minus 0.4, that is equal to 1. So c1 would be 1 divided by 1 minus 0.4, that is 0.6. So c1, that would be equal to, okay, so I'll be having 1 divided by 0.6, that is there. I can write it to be 5 by 3. You can write it to be 5 by 3. So now to have the forced response of the system, that is 5 divided by 3. Okay, so I have 5 divided by 3 as the forced response of the system. Okay, so the next problem what I have here is y of n, that would be equal to, so that is minus 0.5 into y of n minus 1, that would be equal to cos of n pi by 2. Okay, that is n omega, that is there. Okay, so the input is cos n omega plus beta or phi, that is there. I can have the forced response of the system to be calculated like this. Okay, so what happens here to find the forced response of the system? X of n, that would be cos of n pi by 2, that is there. Depending on the input, I have the forced response of the system to be c1 cos 0.5 n pi plus c2 sin 0.5 n pi, that is there. So that is yf. Next, yf of n minus 1. So in place of n, I can write it to be n minus 1. c1 cos of 0.5 pi n minus 1 plus c2 sin 0.5 pi n minus 1. So that is there. Now what I can do here is I can just multiply and I can get the answer depending on it. So I can give this problem as a work to Bhaskar. Okay, I can give this work to Bhaskar and he will be sending the detailed solution to it. So the third one, what I have here is y of n minus 0.9 y of n minus 1 plus 0.2 y of n minus 2. That would be equal to 0.5 power n. So here also you will be having the input as x of n, where you will be having x of n to be 0.5 whole raised to the power n. So that is alpha power n. So where alpha would be equal to 0.5, that is there. So now what I can do here is I can have the characteristic equation in a similar manner. If alpha power n comes into picture, what you need to do is you need to have the characteristic equation being written there. So 1 minus 0.9 z power minus 1 plus 0.2 z power minus 2, that would be equal to 0. Next, z square minus 0.9 z plus 0.2, that would be equal to 0. So where you will be having z square minus 0.9 z plus 0.2 equal to 0 there. Okay, so there you will be calculating the equations, the roots depending on the characteristic equation. So where you will be having that is the roots of the characteristic equation being obtained. So alpha is equal to 0.5 is a repetitive root. What I can do here is the forced response of the system YF of n will be Cn 0.5 power n. So this is the forced response of the system. So this is the characteristic equation what I have. So depending on the characteristic equation, you have the forced response of the system. This is the forced response. So these are the two problems that I'll be giving it. So I'll be giving this to Rahul HV. So he'll be solving it and he will be giving the solution to the given problem. Okay, so these two problems are being there, and we will continue in the next class. Okay, I'll stop it here, and meanwhile see to it that you keep solving certain numerical problems and you will have a better understanding of it. Okay, thank you everyone.